Hello, my name is Christopher Alquist. I am demoing Lab 7. My lab section is Section 4 on Wednesday at 12 p.m. Right here we have my implementation of the subway controller. And I give in my reports a few sections of interest. The first one is where all of the logic for the D flip-flops are given. The Nexus state logic is given right here. The logic for D is implemented right here. And then in the middle here we have our D flip-flops, where we can see I use virtual connections QA, QA, QA plus. And then over here I have all the different inputs inverted to use as different virtual connections. And then over here, this is how I simulated the circuit. I just used, different pulse trains for P1, P2, and clock. V to D is set to 1.8 as we usually do. And when we simulate it, this is the waveform that we have, where we see we have QA, QB, QC, P1, and P2. And we have our clock up here. P1 and P2, of course, are pulse trains, are pulse signals. And so I have that P2 is half the period as P1. And that clock is half the period of P2. So, and then down here we have our output D. Notice how we have both 1 and 0 hazards. Because of this, when I would do the A to D conversion for these waveforms, it looked really not nice, and so I decided to keep it as the square waves here, and that's honestly no problem, because given in my lab report I made earlier this. It's the same, the exact same signal here. It's just earlier I had I put these markers in V1 through V22, and the cadence didn't just save these markers, and so this is the same exact waveform as you see right here. It's just we're going to be using this picture in order to step through it so we can more easily see how the controller is going through each of the states. And so this is what we're going to be seeing right here. No, just to not worry that it is the same exact waveform. It's just this has markers on it, and you can, in my report, you can see that it's I give both of them. So to go through the demo now, I'm going to zoom in here a little bit, and we're going to step through V1 through V22, and I'll be doing this using the truth table that I made for each one of these vertical markers. Each one of these vertical markers is on the positive edge. And so we're going to be stepping through these. I did put the output truth table for these markers in my report. So that's what I'm going to be using to step through it. So before V1, we have two invalid states here. In my state transition diagram, I only go to state 5, and we have states 110 and 111, state 6 and state 7. And those are two invalid states. And the first state that is valid, which is 010, or state 2, is given at V1. So at state 010, we have P1 is 0 and P2 is 1. And from our truth table, we know that the next state that we can expect is 010, and that D should be 1. So that we see D is 1 right here, and we see that our next state is 010, and that for this one we have both P1 and P2 are 00, and that will just hold the state. So we should see 010 again for V3, and D1, D is still 1, and we have next here we have 11 for P1 and P2, and this is technically an invalid input. You can't have both of the sensors being tripped at the same time. That's not possible. So that was implemented as just keeping the same state. And so that's exactly what we see here. D is still 1. The next higher clock edge is 0, 1, 0 still at state 2. And then here we have, for V4, we have P1 is 1 and P2 is 0. And this actually leads you to the next state 3, 0, 1, 1, which is what we see at state 5. We have 0, 1, 1. And right here, 0, 1, 1, state 3, we have P1 is 0 and P2 is 1. And that takes you to state 4, which is 1, 0, 0. So state 4, V6, is 1, 0, 0. And then right here we have both of our inputs are 0, 0, which that just keeps you in the same state. So that's what we see. So we have 1, 0, 0 again for V7. So we're still in state 4. And then we have 1, 1, which is an invalid state, which keeps you in the same place. So that's what we see again. So we have 1, 0, 0. And we have 1, 0, which keeps you in the same state. So we see here, we have 1, 0, 0 for V9. And then we have 0, 1 here for P1 and P2. So 0, 1, which for V10 takes you to state 5, which is 1, 0, 1. So we have 1, 0, 1. So we're in state 5. And then we have P1 is 0 and P2 is 0, which keeps you in the same state here for V11. So we have 1, 0, 1. And then for state 11, for V11, state 5, we have 1, 1, which is an invalid input. So we're still here. And then we have, for V12, we have 1, 0, which resets you back. Well, it's not a reset. It takes you back to state 0. So we see that on the next high rising clock edge, we have state 0, 0, 0, 0 for QA through QC. And then for P1 and P2, we have 0, 1, which keeps you in the same state. And then we stay in the same state 0 for the next few here. So we have 0, 1, 0, 0, 1, 1, which is an invalid state, invalid input, and then 1, 0, and then 1, 0 takes you to state 1. So for state 17, we're at state 1, which is 0, 0, 1. And then we have 0, 1, which takes you to state 2 that we see here in V18. So in state 2, which is at this point, we've kind of come back to what we started at. We started at state 2, now we're back at state 2, and we start seeing things just repeat. It's going to take the same walk through the state machine again. But we'll continue. So we're at V18, so we just entered state 2, and we have 0, 0 as P1 and P2. So we stay at state 2 for V19. And let me just move this over really quickly. So at V19, we're still in state 2, and then the next inputs are 1, 1, which is an invalid input, so we just stay put. And then for V20, we are given 1, 0 here, so P1 is 1, and then P2 is 0. And that takes us to the next state, state 3, 0, 1, 1. So here at V21, we have 0, 1, 1. And of course, D is 1 here. So V21, we are taken to state 4 at V21, and at which we come back here to V22 because we're given 0, 1. We go to V22, which you come back around to state 4. And so we see that from these 22 different steps within the these 22 different high rising clock edges, within this waveform. We start at state 2. The reason why we start at state 2 is because what we've seen before with sequential logic circuits is when you demo them or simulate them, they start at a random state. We saw that this started technically with 2 invalid states until it found its way into a valid state. Once we were at that valid state 2, it continued on the state transition diagram with accordance to how it's supposed to be implemented. It was correct when it traveled through all the different states from V1 to V22, and we see everything kind of just restarting again. We did see that D was the correct output for all the correct inputs, and these logic hazards here would be fixed if we went back and fixed the Boolean equations in order to account for these logic hazards that we see. Overall, we saw that everything was correct. It stepped through each state that was supposed to be the next state given these 2 inputs, and its current state was correct. And we also see that D also was the correct output for every state. This logic 1 or this logic hazard here unfortunately did jump up to be high when it's supposed to be 0, but we saw that generally all these are 0 as they should be, and so this logic hazard here really did not affect anything, because we saw that it's still the circuit still carried on normally. It still carried on how it was supposed to. So yeah, thank you.